The next group of program control instructions that we will discuss is the subroutine group. Let's begin this discussion by talking about subroutines. Here you see a typical computer payroll program. This program retrieves individual salary data and then computes information to be printed on the check stub, such as withholding tax, state tax, savings bond deductions, and health insurance premiums. Each time data is to be printed, the program must execute the same series of print instructions. This identical set of instructions is repeated throughout the program. Obviously, there must be a more efficient method of writing this program. A better method is to use the print subroutine. This subroutine contains all the print instructions necessary to print out characters of data on the check stub. Notice that none of these instructions appear in the payroll program itself. Each time the program desires to print out information, it simply requests or calls the print subroutine. Once the information is printed, the subroutine returns control back to the main program. Typical subroutines are used for such functions as multiply and divide, calculating sine, cosine, and other trigonometric functions, and input-output functions, such as the print operation we mentioned before. Subroutines themselves can also use other subroutines. For example, the main program may call a subroutine to find the square root of a number. Finding the square root may require any number of divisions. Therefore, if the system does not have a hardware divide function, the square root subroutine calls a divide subroutine each time a division is required. After each division, control is returned to the square root subroutine until the square root has been calculated, at which point control is returned to the main program. Programs may also share subroutines. Here you see the main program, an I/O service program, and an error routine program, all requiring use of the same print subroutine. When dealing with subroutines, the computer has two problems. First, the main program must tell the central processor where the subroutine is located. Secondly, the subroutine must be able to return the CPU to the proper point in the main program so that the program can continue where it had left off. How are these two problems solved in a PDP-11 system? These problems are solved by two subroutine instructions. JSR, or jump to subroutine, which is used to find the subroutine, and RTS, or return from subroutine, which is used to return control to the main program. As we will see shortly, these two instructions are closely related. We will first talk about the JSR, or jump to subroutine instruction. This instruction allows the main program to jump to a specific subroutine. If the program jumps to a subroutine, it has to have some method of knowing where to return in the program once the subroutine is finished. The JSR instruction causes the program to jump to a subroutine and at the same time constructs a linkage pointer. This linkage pointer allows the main program to continue where it left off once the subroutine has been executed. This is the format of the JSR instruction. The first part of the word is an opcode. As in most other instructions, this indicates what to do, what operation to perform. The second part of the word is a linkage pointer that serves to remind the program where it was prior to the time it jumped to the subroutine. The third part of the word is the subroutine location itself. This tells the main program where it must jump to in order to use the subroutine. On the instruction card, you will notice that the JSR instruction is signified by 004 RDD. Let's analyze this code. The 004 in bits 9 through 15 indicates the opcode for a JSR instruction. R indicates a linkage register specified by bits 6 through 8. This may be any general purpose register in the PDP-11 except R6, the stack pointer. The DD indicates the two fields of a destination. Notice that the fields are addressing mode and selected register. That's right, this destination is identical in format to the destination operands we've discussed before. Caution must be used when selecting the two registers in a JSR instruction. Although any register except R6 can be used for the linkage pointer, and any register can be used for the destination, the same register cannot be used for both. For example, you can use R5 for the link and R4 for the destination. However, you can never use R5 for both the link and destination. When using a subroutine, we use a JSR instruction to jump to the starting address of the subroutine. This starting address is specified by the destination portion of the JSR instruction. Once the subroutine is finished, we want to go back to the next instruction in the program that would have been executed had a JSR not occurred. The RTS instruction returns control to the proper point in the main program. The destination field portion of the JSR instruction allows the program to find the destination or the starting address of the subroutine. Remember, this destination field consists of an addressing mode used in combination with a general purpose register. The destination field allows the CPU to locate the subroutine starting address. This starting address is moved into the program counter, thereby causing the jump to the subroutine. However, notice one problem. The PC currently holds the address of the next instruction in the main program. If we move something else into the PC, we'll lose that instruction location and never be able to return to the proper point in the program. Therefore, we must first save the current PC before loading in the new PC for the subroutine. We can save the main program PC by moving it into the link register. However, we again have a similar problem. The register specified as the link may have data that is pertinent to the main program. Therefore, we must also save this data before we can load the link register with the PC. We save the former contents of the link register by simply pushing it onto the hardware stack. This, of course, means that the stack pointer will also move to point to the latest entry on the stack. Now you can see why we must never use R6, the stack pointer, as the link register. At this point, these conditions exist. The contents of the link register have been saved by pushing them onto the stack. The current PC, or main program PC, has been stored in the link register. This will allow us to find our way back to the main program when the subroutine is done. And finally, because the PC is now empty, we can load the subroutine starting address into the PC and jump to the subroutine. We use the mode and register fields of the JSR to find the subroutine starting address. The subroutine starting address is then moved into the program counter. Because the PC now contains the starting address of the subroutine, the computer begins executing the subroutine. You've probably noticed by now that the JSR instruction does many different jobs. It first saves the contents of the link, then saves the old PC, and finally loads the subroutine starting address to make a new PC so that the subroutine can be executed. Let's look at these jobs one at a time and see how the JSR does them. The JSR first finds and saves the subroutine starting address. In this example, the destination field tells the CPU that register R3 contains the starting address of the subroutine. Once found, this address is saved by holding it in a temp register. This temp register is internal to the processor and is not accessible to the programmer. Now, the JSR must save the contents of the register which has been selected as the link. The link field of the instruction specifies a register, in this case R5, to be used as a link. Therefore, the contents of R5 are pushed onto the hardware stack after the stack pointer is auto-decremented. The JSR next wants to save the current PC. The link field of the instruction has specified R5 as the link register. It is now empty because we've saved its contents on the stack. Therefore, the JSR takes the main program PC and moves it into the link register to save it. The final step performed by the JSR instruction is to load the subroutine starting address into the PC. Remember that the destination field directed the CPU to the subroutine starting address stored in register R3. This address was then stored temporarily in the temp register. At this point, the JSR takes the contents of temp and moves it into the PC. In effect, it has loaded a new program count. The processor can now begin executing the subroutine. Now, let's discuss the RTS, or return from subroutine instruction, which takes advantage of the link to return control to the main program once the subroutine is finished with its job. The RTS format is relatively simple. It has an opcode telling what to do or what operation to perform, and it has a linkage pointer that allows the CPU to return to the proper point in the main program. The code for an RTS instruction is 00020R. The 00020 in bits 3 through 15 specifies the opcode for an RTS instruction. The R indicates a link register specified by bits 0 through 2. Use extreme caution when selecting a register for the RTS instruction. It must be the same register that was used by the associated JSR. Why is this so important? When the JSR causes a jump to the subroutine, it also causes the contents of the PC to be stored in register R5. In other words, R5 is used as our link register. Upon completion of the subroutine, the RTS instruction directs the CPU to the address contained in register R5. If the same register is used, in this case R5, then it returns the processor to the next address in the main program. RTS R5 is a typical return from subroutine instruction. Its prime function is to restore information. It first restores the PC by moving the old PC from the link, in this case R5, into the program counter, R7. It then restores R5 by popping the data off of the stack and moving it into the link. At this point, everything is just as we found it prior to execution of the JSR instruction. In summary, then, we can say that a JSR is used at any desired point in a program to cause a jump to a specific subroutine. We can also say that every subroutine must end with an RTS instruction to return control to the proper point in the main program. That completes our discussion of subroutine instructions. Now, let's discuss the next to the last group of program control instructions, interrupts and traps. There are three methods of exiting a main program. The first is a software exit in which the program specifies a jump to some subroutine. A second exit can be caused by internal hardware, which detects certain error conditions and issues a trap, forcing a jump to an error handling routine. A third exit can be caused by external hardware, which initiates an interrupt, forcing a jump to an interrupt service routine. Do you remember this diagram? Here we showed you how a JSR instruction could be used to jump from the main program to a subroutine. Once the subroutine was finished, an RTS instruction could be used to cause a return to the proper point in the main program. What about an interrupt? As you can see, an interrupt is very similar to a JSR. As soon as the current instruction is completed, the interrupt causes a jump to the start of a service routine. Once the service routine has been executed, it causes a return back to the proper point in the main program. How about a trap? Notice how similar a trap is to an interrupt. The trap causes a jump to an error routine. Once this routine is completed, it returns control to the main program. When an interrupt occurs, it forms a link back to the main program. However, it does it differently than a JSR instruction. An interrupt simply takes the current PS word and the current program counter and pushes them onto the hardware stack. The CPU then retrieves the new PC and new PS that are part of the interrupt vector. The new PC points to the start of the interrupt service routine, and the new PS establishes initial conditions required by the interrupt routine. Let's take a closer look at how the CPU finds the interrupt routine. Whenever a device issues an interrupt, it also supplies the CPU with the address of its own interrupt vector. This interrupt vector directs the CPU to the starting address of the device's interrupt service routine. The CPU then retrieves and executes the service routine. Once we've gone through the entire service routine, how do we get back to the main program? How do we return? Returning to the main program is accomplished by a single instruction, RTI, return from interrupt. The RTI format is very simple. The entire instruction word is an opcode of 000002. An RTI instruction restores the main program by simply popping the program PC and the PS word from the hardware stack. Remember, these two items had been pushed onto the stack by the interrupt. Another way of returning from an interrupt service routine is by using an RTT, or return from trap instruction, which has an opcode of 000006. The RTT performs the same function of popping the stack as the RTI instruction. How do the RTI and RTT instructions differ? Well, the RTI instructions allow us to use the T-bit in debugging a program. The RTT instruction, on the other hand, inhibits the T-bit so that no program debugging can take place. We're not going to discuss the T-bit at all in this course. However, there is an explanation in the processor handbook we gave you. Whenever dealing with interrupts, the programmer has three special duties that he must perform. First, he is responsible for writing the interrupt service routine. Secondly, he must make sure that the service routine ends with either an RTI or RTT instruction so that the computer can return to the main program after completion of the service routine. And finally, he's responsible for loading the desired PC and PS into the appropriate vector locations. In addition to interrupts, the CPU uses internal traps to service errors such as non-existent address or power fail. There are actually two types of traps. A hardware trap is caused by an error condition that is detected by internal hardware. And a software trap is caused by a trap instruction. In either case, the program jumps to a special handling routine. When the CPU detects certain predetermined error conditions, it first causes the program to stop by issuing a trap, and then tells the program to jump to an error handling routine to fix the error. Thus, errors found by internal hardware cause a trap to an error routine. A trap is similar to an interrupt, except that it is initiated by the CPU rather than an external device. When a trap occurs, the PS word and the current PC from the main program are pushed onto the hardware stack. In this respect, operation of a trap is identical to interrupts. A trap vector then directs the CPU to the starting address of the error routine. Thus, a trap vector functions in much the same way as an interrupt vector. Once the trap has caused a jump to the error routine and the error has been corrected, how do we return to the main program? We return in exactly the same way we did when we had an interrupt. We can use either an RTI or an RTT instruction to return to the proper point in the main program. Remember how we said that a software trap could be issued by using a trap instruction? Let's now look at these trap instructions. For example, we have an input-output trap instruction. The opcode for this IOT instruction is 000004. The instruction is used by the I/O executive routine. This executive program automatically handles some of the more routine functions of the various I/O devices. Another instruction is the breakpoint trap, or BPT instruction, which has an opcode of 000003. This instruction is used by debugging aids in the software package. There are two other groups of trap instructions. These instructions use opcode 104000 through opcode 104777. Rather than take the time to discuss these more specialized trap instructions here, we'd like you to refer to the workbook if you want to know more about these instructions. All trap instructions function in an identical manner. However, each instruction uses its own vector and therefore causes the program to jump to a different handling routine. Let's review what we've been talking about. Traps are initiated internally. Interrupts, on the other hand, are initiated by external devices that need to be serviced. There are two types of traps. A hardware trap is caused by an error condition that is detected by the CPU. In contrast, a software trap is caused by a trap instruction that is part of the program being executed. Both traps and interrupts first save the current PC and PS of the main program by pushing them on the stack, then find the required handling routine by means of a vector. Finally, once the routine has been completed, Return to the main program is accomplished by either an RTI or RTT instruction, which pops the program PC and PS off the stack. Now, let's discuss the very last group of program control instructions, the miscellaneous instructions. This is a nice way to finish up the instruction set because there are only 5 miscellaneous instructions. 2 you already know, 3 are new instructions. Remember this. In the very first part of this study unit, we showed you a 2-instruction program that cleared the entire memory. The last instruction, branch -2, returned us to the previous instruction, which had been cleared out. Remember what we said? All zeros is the opcode for a halt instruction. Do you also remember what we said about condition code operators? We said that if there is a 0 in each condition code select bit and a 0 in the operator bit, then nothing can happen. There is no operation. Therefore, this particular opcode of 000240 is the code for a no-op instruction. A no-op instruction might be used if an entire program had been coded and then, for some reason, an instruction was deleted. Rather than recode the entire program, a no-op could be used in place of the deleted instruction. Now, let's look at the 3 new instructions. One of these instructions is called reset and has an opcode of 000005. The reset instruction places an initialized signal on the unibus so that every device tied to the bus is initialized to the same state it held when power was first applied to the system. The next instruction is the wait instruction, which has an opcode of 000001. The wait instruction forces the CPU to release control of the unibus and not re-establish control until after another device has been serviced. In other words, the CPU must wait for some external device to grab the bus and interrupt the CPU for servicing. The last instruction is jump, which is a single operand instruction causing the program to go to a new location. Notice the format: an opcode specifying the jump and a destination field specifying the location to jump to. Notice the difference between the jump and the unconditional branch instructions. Although the branch instruction causes a jump to a new location, it can jump no more than 177 locations forward or 200 locations backward from the program counter. On the other hand, when a jump instruction is used, the program can jump to any location desired. That concludes our discussion of the PDP-11 instruction set. Now we'd like you to complete the remaining study exercises contained in your workbook. When you hear the next tone, turn off this playback unit and complete the exercises contained in your workbook. After you've completed these exercises and checked your answers, you can proceed to the next study unit.